requested to extend their cooperations by muting your speaker and camera because in between some disturbance will be going on. That's what we are giving the request. Please don't mistake into us. Now I request Dr. B. Devibala, Assistant Professor, Department of Chemistry, Muhammad Sadaq AJ College of Engineering, Siruseri, Chennai, to introduce our chief guest.
Very good noon to one and all present in the online digital meet. I am very much delighted to introduce our today's guest speaker and my institute senior, Dr. P. Muthumareeswaran from Anna University. Welcome, sir. He got his doctoral degree from Madurai Kamaraj University under the guidance of Dr. S. Rajagopal. Later, he did his postdoctoral research from Korea Advanced Institute of Science and Technology, South Korea. Later, he joined as a DST-inspired faculty fellow in Alagappa University, Karaikudi. He is currently working as an assistant professor in Anna University, Chennai. He has totally 14 years of research experience and published more than 60 journals and 4 book chapters with totally of 600 citations. He completed various research projects from DST and RUSA. He has been reviewer of so many international journals like Journal of Inclusion Phenomena, Analytical Letters, Journal of Molecular Liquids, Langmuir, Chemistry Select, Material Today, and so on. He is a member in various professional societies, Indian Society for Radiation and Photochemistry, and many more. He has delivered more than 20 invited lectures and talks in various conferences. With a short note, I request Dr. P. Muthumareeswaran to take over the session. Over to you, sir.
Thank you, Dr. Devibala, for the nice introduction. First of all, I thank Muthumareeswaran College of Engineering for giving me this opportunity to deliver my notes. Muthumareeswaran College of Engineering is very a close relation with me because it is first started in Kilakale, which is nearby to my native place, Kamudi. Many of my friends have graduated from this Kilakare Institute, and now it is in Chennai. So I'm really happy to give a talk in this institute. And I request Dr. Devibala to share the slides. Hello.
I'm sharing the slide. It is not visible.
Yeah, it's not visible. Please. So it's not possible. Is there any problem in sharing slides?
Sir, no, we could see.
Sir, screen is visible, sir.
But not, it is not visible
Yes,
to me.
sir. Screen is visible.
Okay. I don't know what happened because it is not visible to me. I will try to share my screen, okay, from my mobile itself. Huh? Is that okay? Please
okay, sir. I will stop. Slides. I will stop my presentation. Then you start yours, sir.
And I will share the screen. Okay. Right.
Okay, sir.
Thank you. Can you see my presentation?
No, sir, your mobile screen only visible. Now it is started showing, sir.
Yeah, okay.
Yes, sir.
I'm sorry. Can see my slide. Can you see?
But it is looking very small, sir.
Hello? Very small.
Yes, sir.
So, it's read. Daily Bala, is it visible?
Sir, it's a in mobile screen. It is showing very small inside the mobile. Very small. Is there any zoom option or presentation option?
I'm, I'm now.
Otherwise, shall I give one try, sir? Shall I present your? Shall I present your screen once I will check?
Yeah.
Okay, sir.
Yes, yes. Start.
இல்ல அவர் இருக்கும்போது ஷேர் நான் கொடுக்கட்டா?
I have stopped my sharing. You just make your presentation share. So have you shared your screen?
Sir, not yet, sir. Just we're trying, sir. Just few minutes, please.
Yeah. Yeah. Thank you.
Sir, were you able to see the screen?
Not now. So,
Sir, would you mind going out of the call and logging in again?
yeah, sure. Now the screen is visible to me.
Okay, sir.
Please put your PowerPoint in a presentation mode. Yeah, thank you. So thank you for the cooperation of organizing committee because I'm just presenting from outside. It is not possible for me for sharing from my laptop. So today's topic is photochemistry and its applications. So we can straight away go to the presentation. Okay. So please next slide, please. Next slide, please. So first of all, we will start with a brief introduction of photochemistry. So what is photochemistry? So what is photons? So all we are seeing in this world from with our eyes. Okay. So how this vision is working is nothing but photochemistry. So when a light wave or any electromagnetic radiation which is interacting with any body that is which is having mass is called the interaction of light with mass. Okay. Therefore, the interaction of electromagnetic radiations with this mass, that is physical entity, which is giving some changes, is called photochemistry. Okay. Sometimes it may called as photophysics as well, because it is involving various pathways and changes. Okay. Then sometimes it is also known as photophysics. Okay. So what is photon? So where the photon and photon, these words are coined. Okay. So photon is nothing but packet of energy. So when the light is having certain wavelength and certain wave number, if you reciprocate that wave number, it will give into the energy. That is E is equal to h mu. Okay, or h c by lambda, where it has certain energy. So while the analysis of light, that is which is in the form of waves or how it is propagated through the space, that type of experiments are progressing in the olden days. It was coined that there is no any possibility. It's not possible to propagate a light wave or a sound wave without any medium. But we know very well that the sunlight is reaching here. In between is a vacuum. There is nothing in between. Okay. Even though our atmosphere is here, it is very limited. So in between the sun and the earth there is nothing. It is vacuum. So how the light is propagated without medium, if it is wave character? Then there is a theory which is called the quantization of theory, emerging from quantum mechanics. The light is not a continuous wave entity, it is a quantized entity which is called quantas. That quantas is called photons. Okay. So next slide, please. So this is the basic property of the light, and we can see how the light is working with and what is the visible light spectra. So how we are seeing, what is the meaning of our vision? It is nothing but chemistry of cis-trans isomerization. Okay. So in our eyes, we have one chemical compound which is called retinol, which undergo a cis-trans isomerization between the energy gap of a wavelength 400 to 700. That is, it is not exactly 400. It's up to 300 to 750 or 800 nanometer. Okay, this is called the visible range of spectra. So what is happening in this type of in this range of spectrum? There will be a cis-trans isomerization, and isomerization will take place with each wavelength with rotation. Okay, that's why we have vision in our eyes. So without interaction, without that is after that range of this wavelength, it is not possible to make a transition of retina. Therefore, we don't have any vision in this out of this range. Okay, this is the basic concept of our vision. It is nothing but a photochemistry. The first application of photochemistry. Okay, next slide, please. So you can see that the range. So the range of electromagnetic radiations is starting from radio waves to X-ray, via microwave, far infrared, near infrared, visible, ultraviolet, and vac violet. That is X-rays and gamma rays. Okay, but this isomerization, which is responsible, which is due to the range of 400 nanometer to 800 nanometer, which is ranging from 149 kilojoule per mole to 299 kilojoule per mole. This is the range of energy. Okay, beyond that energy, it is not possible to recognize from with our eyes. Okay, therefore this is called the visible range. Next slide, please. So what are the interactive properties of light with media? Okay, there are several phenomena which can under when the light is hitting on material can uh, undergo. Okay, so a light which is when it is falling on some matter, it may be a solid or a liquid substance. First one, it can transmit the radiation. That is, if it is transparent and it is not going to blast that radiation, then it can allow the radiation. For example, mirrors and some polyethylene type of fiber glasses will allow the light, electromagnetic light, visible light. But at the same time, if you clearly watch it, some ultraviolet rays are blocked by this material. Okay, that's why we are wearing ultraviolet protected glassware, eyeglasses. Okay, and this phenomenon is called transmission, and the another one phenomenon is absorption. The light is absorbed by the material. Okay, how it is absorbed, we will see in the slide. And radiation, refraction, reflection, string. Okay. These four phenomena is there, and we have to understand what is the basic difference between these all phenomena. One is reflection. Reflection is an elastic collision which is coming back when the light is hitting on the substance. It is coming back to the source, towards the source. Scattering means it will scatter. There is no any direction because it will scatter in all directions. Reflection means it will deviate from the path. Okay. For example, if you have some water, if you shine the light will deviate from the path. That is called reflection. And what is emission? There is always a confusion between reflection and emission. Reflection means when the light is scattered, it is not absorbed by the substance. But at the same time, emission means when a light is absorbed by the molecule and there will be a molecular change inside the molecule and it will re-emit light. That is called the emission. Okay, so we should not confuse between emission and reflection or refraction scattering. Okay, the next slide. Next slide, please. Next slide. Yeah. So
Yes,
we
delay, sir.
absorb. Yes.
There's some delay, sir.
Yeah, okay, no problem. So the basic law of absorption is called the Lambert's law, and some other scientists also have joined with the Lambert's law, and then it is finally called Beer-Lambert's law. So, what is the Beers and Lambert's law? So when you light shine light on the substance, uh, maybe a monochromatic light, okay, it's a homogeneously absorbing medium, then the equals of fractions of light absorbed by the successive layer, okay, is proportional to the incident light, that is absorbed light. So if you layer by layer, okay, the thickness responds to the, that is proportional to the absorbed radiation, okay, that is called the Lambert's law. And the Beer's law is nothing but, next slide please. Next slide. Right. Equal fractions of incident radiations are observed by equal changes of concentration. Okay. So both Beer's law and Lambert's law are combined to give Beer's-Lambert's law, where the absorbed light is proportional to thickness of the pathway as well as the concentration of the substance. Okay. This is called the Beer's-Lambert's law. Next slide, please. So then what is called the photoexcitation? So for photoexcitation, we should think of what is the interaction between the radiation, electromagnetic radiation, and matter, which is maybe in a solution state or a solid state or a gaseous state. Okay. When light is interacting, that is electromagnetic radiation is interacting with light, with matter, several pathways will try to happen. So we will start from uh, microwave region. Okay, so it's the lowest wavelength. So what microwave will try to make a level is a bit higher than the infrared. Try to the, for example, if you have a rubber band between this two, between your putting inside 2 points, okay, you just vibrate that rubber band, what will happen? It will vibrate, but the 2 points will not change. Okay, this is how the light is interacting with the orbital electrons in the orbital. It will interact with the orbital electrons in the orbital, and it will relocate the orbital to pi star, or sigma to sigma star, or n to pi star, and then it will reorganize itself and come to the original position and become normalized. So the absorbed energy will be utilized to relocate the orbital, and it will come to the original position. At that time, the absorbed energy will be released. Okay, the state at which the orbitals is disturbed using the external light is called the excited state, and the reactions are and this phenomenon is called a photoexcitation. Okay, so the excitation may be it will undergo so many pathways like fluorescence and phosphorescence. You can see it one by one. Okay, next slide. So this is the Morse diagram, energy diagram. So when the light is absorbed by a molecule, the orbital overlap the orbital, that is molecular orbital between two atoms is disturbed, and it will make a small disorientation, that is disturbance will happen inside the orbital. But at the same time, the molecule will not dissociate. The internuclear distance between two atoms is not disturbed. That is what's called the Born-Oppenheimer approximation. And that's why we don't have molecular dissociation of molecule with deviating time of impact with light. What will happen? So all the materials in the world will dissociate. There is no living organism. Okay. Something happened. Let's wait for the to share the slide. Okay. So next slide, please. Okay, we shall start. So this is called the Jablonski diagram. Okay. So it is a similar diagram with Morse diagram. That is the energy level diagram. Okay. The energy when the light is absorbed by a molecule, it may undergo several pathways. If it is a pathway which is Okay, I will discuss about the Jablonski diagram. Okay, you have already seen the diagram. And there experiment will talk about the Jablonski diagram and the basics. Okay, so how the Jablonski diagram is designed. So we have some uh, zero state, that is lower energy state. So what is the lower energy state? When the energy is absorbed with mod, it's in it is intrinsic energy level, then it is called zero energy level state, that is a zero state. So when the light of the molecule go to even on Oppenheimer estimate telling that the internuclear distance is not altered. So orbital this is a real like okay. The only thing of vibration okay. Because zero vibrations that is 0 degrees Kelvin so have some vibration state. Some vibration will be there even at the 0 Kelvin, it is absolute zero. That is called the 0 point energy. So any molecule will have its own vibration even at the 0 Kelvin, that is absolute temperature. Then at the time of the excitation also, when the absorption also their own therefore zero state and excited state, this absorbed state will have some vibrational state, and the first excited state will also have some vibrational state. Okay, so at that point, you also noted that the excited molecule may go whatever may be the vibration state. Okay, so reaching of that is coming back to the zero energy state may due to the some radiative decay, that is it may give back the energy observed as a emission, radiative energy or non-radiative energy. But the observed molecule will go to the some other vibrational state. That vibrational state will have to dissipate its energy as a heat, that is heat energy. Then it will come back to the original state. Then it is called radiation-less decay. Okay. So we have given here so time scale for the all these processes. That is for the light absorption process, it is around 10 power 15 per second. Okay. When the electron is excited to the first excited state, the vibrational state, whatever it may be, it will come to the zero vibrational state of the first excited state. Then it is called internal convert. Okay. Then if it is going to the triplet state, then it is called intersystem crossing. If it is a radiative decay from the zero vibrational state of the first excited state, then it is fluorescence. If it is from the triplet state, zero vibrational it is fluorescence. Okay, these are the several pathways, and you can we will see the in detail about these pathways in the next slide. Next slide, please. So please go to the next slide. It is the repetition. Next slide, please. Next slide. Okay. So Caruthers and Rappers are the basic fathers of photochemistry, and the is absorbed by a substance in order for the photochemical reaction to take place. That is why that is absorbed. So it will make some reaction change. It's called, it is the basic of photochemistry. That is first part. It is observe a molecule. Next slide, please. Next slide. Yeah. So then the second state is, sorry, previous slide. The second law of photochemistry is Stark and Einstein's law. The quantum of radiation observed by the molecule activates one the primary step of photochemical process. That is, it will primary molecule is the primary step of chemical process. The second law of photochemistry. So what is the first law? You have to observe light. The light is observed to make some change. The second law is it will activate one molecule. Okay, one photon of light will activate one quantum of this one molecule. Activate one for a primary process. Next slide. Okay. So this is activation of one molecule by some amount of energy with one quanta is called one Einstein of energy. Okay. This given by this equation, and it may be sometimes one photon or maybe sometimes with multiple photons. Okay, so one photon will activate one molecule, and the another the same molecule and make the uh, still higher state. Okay, so these are the processes because multiple photon processes because it is used in photon up conversion reaction. Okay, next slide, please. So when the light is observed, it may undergo several reactions. It may dissociate into radicals. So, for example, starting light with it cleaved as a radical, theta. Okay, if it is cleaved by light, maybe by radiation, it is called pulse radiolysis reaction. Okay, if it is not clear, but at the same time it is disturbed, it will some of advanced in photometry, and it may lose one electron. Okay, and this is called photoionization. Sometimes it will attach with some molecule, and sometimes it may rearrange, like our retinol. That is called photoionization. So these are the primary photochemical process. The photon is observed by a molecule. This right? There is Bala. Next slide, please. Yeah. So the energy transfer when the molecule is excited, it may be happen in some other way. That is, if the molecule is excited and it may give its energy or a electron. Okay. Sometimes the excited molecule will give energy to nearby molecule, which is called the quencher or a sensitizer. Quencher means it will reduce the reaction. Sensitizer means it will get excited, otherwise it will uh, take up energy from that excited molecule and it will go some other catalysis reaction or some other photochemical processes. Okay, then it is called a sensitizer. Sometimes the molecules, when the molecular concentration is very high, the molecules collisions will be very high. The frequency of collisions will be high. Then the molecules will quench itself. That is called auto collision. So that we will try to keep our concentration very low as much as possible. For example, if you are taking a UV spectra of a molecule which is going to regarded as a emission spectra, the OD should be below 1. Otherwise, the auto quenching will play a big role in your photochemical reaction. Okay, next slide. So the kinetics of these processes are studied using some decay kinetics, and the kinetics rate law can be given by K into IEA, that is uh, formation of activation process. That is, we know all that from the kinetics. The slow state is the rate determining step, which is called the steady state approximation. So in photochemistry also, the slow step is the rate determining steps, since all the other steps are very fast steps. Then the transition state formation will be the rate determining. Okay, next slide. And we will move on to the next slide because time is running out. We will go to the application part very fast. Next slide. Okay, please keep this one. Quantum yield. So what is the quantum yield? So the quantum yield can be calculated in various ways by various techniques, and we will make a general conceptualization on quantum yield. Okay, so the work which should be done, maybe whatever may be the work. Okay, how much of energy is much of observed by a molecule, and how much the work will be done by the molecule. It may be a emission, it may be a catalysis, it may be a sensitizer concept, whatever it may be. So what is the outcome? What is the input? So how much output you are getting? That is called the quantum yield. Okay. So here we have stated ratio between the number of molecule reactants consumed by formed. Okay, this is for the reaction, photon reaction. If it is an emission process, how much amount of energy is observed and how much it is emitted. Okay, if it is a photo rearrangement process, how much molecules or how much light is consumed, how much molecules are rearranged. Okay, likewise we can do that process. Next slide, please. So this is the energy efficiency, that is how much light is preserved over the light. Okay, so what is the chemical process? What is the chemical reaction by observing? So it is trying to convert some chemical into some other form. Okay, if it is a conservation of energy, then it is called light energy consumption. For example, in photosynthesis, what is happening when the light is absorbed by one molecule? Okay, I will discuss in the photochemistry of photosynthesis in the consecutive slide. The amount of energy which is conserved in the form of glucose by absorbing some amount of light is 2870 kilojoules per mole for a single molecule. It is conserving this much of energy as a glucose. Okay, so next slide, please. This is a biological application and a natural application. This is natural or other recent applications. Okay, this is the structure. Okay, you will observe light. And next slide, please. So how the thing is? This is a dark reaction and a light reaction. You can see the I will explain the whole process. Next slide, please. Okay, this is what I need. So we have two photosystems, photosystem 1 and photosystem 2. We have already seen that structure and what is dark reaction and what is light reaction in the previous slide. Okay. PS1 and PS2 is also, always having the same chlorophyll molecule with the same structure. Okay. But the nearby functionalities is totally different. PS2 is getting absorbed by absorbing some light, and PS1 is also getting absorbed light and getting excited. Okay, and it will PS2 is transferring one electron towards a nearby quinone called quinone 1, quinone 2, CO5 that type of electron acceptors. Okay, this charge. One also it is also on transfer electron. Okay, so electron from the PS will fly PS1, so the PS in oscillation state. Electron in that tyrosine is attached with the calcium magnesium cluster in the leaf. So there are many tyrosines are attached with the calcium magnesium cluster. Therefore, the OH bond is very loosely bound since it is hydrogen bonded with that cluster. The electrons can be easily transferred to PS2. Therefore, that system will be stabilized. Now the positive charge is transferred from PS2 to calcium magnesium cluster. Likewise, there will be so many chlorophylls which is attached with that cluster. Therefore, very weak positive charge is accumulated in the calcium magnesium cluster, where where the water molecules will come. Okay, the water molecule will be oxidized, and the oxygen is released, and the hydrogen is transferred to Calvin cycle by a proton transfer membrane. You can see that one electron is transferred and moved towards Calvin cycle from one part to another part. Okay. On the other hand, one proton is transported through proton transfer membrane to Calvin cycle. Okay. In that Calvin cycle, you will have the carbon dioxide which is observed from the atmosphere. Using that electron proton, the carbon dioxide is reduced to glucose molecule. Okay, this is the whole picture of photosynthesis, which is the best application of light reactions. That is natural application, and you can see that there is a transport of electron and proton parallel way, which is similar to a charge separated state of molecule. That is nothing but electromotive force. There is a flow of current. Okay. By this inspiration, we can do several things by applying this same concept artificially. Okay. Next slide, please. Next slide, please. Next slide, please. Yeah. So we can mimic this system by several pathways. Okay. One is to conserve energy from the sunlight. We can utilize that light to make a electron, that is electricity. That is nothing but solar energy radiation. Okay, that is that is why we are having solar panels. But the solar panels are very costly because it will involve in cesium type of materials where the light is shined on a material, the electron is injected and the EMF will be generated. Okay. Uh, this have starting from point from the Einstein's experiment. And another one is oxidation of water. So splitting of water will result in H plus and O2 oxygen. Okay. So it can be preserved, separated and preserved and used in the fuel cells to generate back the energy. So the energy will be generated at the mixing of hydrogen and oxygen with a spark. It will explode. Okay. So it's an explosion reaction. We will get energy. By controlled explosion, we can get energy. Okay. This is one type of reaction, that is photolysis of water using some other electrodes and splitting of water and conserving energy. The other part is mimicking photosystem 2 or making. Okay, this is also one part, and we also can utilize this pathways towards not only towards solar cell, also some photodetectors and photoelectrodes and some other applications. Okay, next slide, please. So these are the examples of photochemical reactions. You can read yourself because it's time is running out. We will go to the next slide. Straight away to the application. This is we have to study another one phenomena which is called the luminescence. Then what is the difference between what is fluorescence or phosphorescence or luminescence? So if any molecule which is absorbing light and giving back its energy in the form of radiation, then depends upon the time delay, it may be classified as a fluorescence or a phosphorescence. Suppose if the light is not emitted by absorbing light, then it is called luminescence or illumination. Okay, illumination is a word, basic word. From that word, we will get luminescence. Okay, there are so many luminescences is there. Chemiluminescence, bioluminescence. Okay, next slide, please. Next slide. Okay, the important application of emission of light by luminescence is laser. So what is laser? So you are exciting electrons to a excited state. Okay, keeping that electron and accumulating that, populating that excited state without giving energy back. Okay, so you are populating that excited state, and at one later you are to deactivate the excited state, and the energy is given at impulsive way. Okay, at the same second, all the excited state electrons is coming to a ground state. Okay, this is called the stimulated emission. Okay, then the light, outcoming light will be very sharp and will have high intense and high energy. Okay, this is called laser. If you are populating that positive and negative charges in between the two diodes, okay, some semiconductors, then the population is the light is as much as intense to the laser, but it is not that much level to the laser. Then it is called the LED. Okay. So next slide, please. Next slide, please. So this is laser application. And next slide, please. These are the various applications of photochemistry. We will see it one by one. We will start from the LED devices. Next slide, please. Next slide, please. Right, this one. So in the previous slides, we have seen there are so many applications. Okay, all the applications are semi-luminescence applications. Okay, so we will start from the LED light. So what is LED light? These are PN junction. Okay, then there will be a positive and negative charges semiconductors, which is fixed in between. Okay, so what will happen? There will be a positive pole will be generated nearby, and there will be a negatively charged particle. Okay, at one junction, it will try to recombine itself to give back energy. That is chemiluminescence. So this energy will be in a high amount of energy. Mostly it is in the UV region. Then there will be a phosphor material which is coated on the cover. Then the light will be observed as the illumination of UV light. That is called illumination of phosphor. That is luminescence from the phosphor. Okay, this is how the LED device is working with the electricity. So it may be called as a electrochemiluminescence. And also the next slide, please. So OLED devices. So what is OLED devices? What is first television? What is the television and your tube lights? So there will be a UV light which is generated by the discharge of heavy metals or neon type of argon type of gases. When it is with a low concentration, then they are biased with high voltage, then they will release UV light. That UV light will be shine phosphor material and it will give light energy. This is the basic concept of tube light. The same thing happened in the television. In the television screen, there will be a phosphor coating and there will be some electron deflection plate. Okay, then your electron will be injected on the phosphor material, then it will glow. It is the application of electroluminescence. Okay, you can see that electrode gun and phosphor material in the old televisions. For the old people can remember that if they will take some magnetic substances nearby that screen, then the image will be deflected. Okay, and then there will be some advancements will come, and there will be a backlight substance, and crystals are developed on the backlight, and the orientations of crystals will produce some images. Then it is called LED devices, LCD devices, that is liquid crystal displays. They are very famous a few decades ago. Now it is LED, organic light emitting diode device. So we can see that PN junctions and the LED light, which is of inorganic materials, we can do the same thing in the organic materials sector. That is, we can develop some organic polymers which can be conductive, sometimes positive and sometimes negative carriers. Okay, then these two carriers can combine to give emissions which is of a particular light. It may be a blue LED or a green LED or a red LED. Okay, these LEDs are packed in a tiny way, maybe on one by one on another. Okay, the combination of these three LEDs will give some particular color. The variations in the color, in the intensity of light can be adjusted by electrically. then the color intensity will differ, and that one point is, then one dot is called pixel. Okay, when you reduce your pixel size, your image clarity will be high. Okay, this is the basic concept of LED device. Next slide, please. This is the application of electroluminescence. So how the conductivity is happening? So when the organic polymer, which is clamped between two biases, okay, mostly they are pi conjugated polymers. Okay, when the bias is applied, the double bond shift will take place towards the negative charge. Okay, therefore, this is how the bias inside the LED device will work. So the conductivity will work. Okay, after that, it will be clamped between two charges, that is positive, negative charged LEDs, then to make the light is possible. Okay, next slide, please. Okay, so when light is absorbed, that is emitted by a by a OLED device, then we can see that it is a photoluminescence, that is, it may be a LED light or it may be a LED screen. Okay, maybe a tube light. Okay, the reverse also can take place. Suppose we have a conductive polymer. Okay, some light is coming to that polymer device, and you can measure the light, how much the light is absorbed. Okay, that is called photo detector. The reverse of the uh, application is photo detector. Okay, biased semiconductor devices. Okay, next slide, please. It's a solar energy cells. That is, we are coming back to the uh, original pathway. That is how the solar energy can be conserved. That is by means of some solar panels we are conserving, but it is very costly. So the highly developed applications of LEDs and OLED devices, that is from the beginning it is LEDs, inorganic LEDs, then it is converted into organic LEDs. That organic LEDs can conserve. So what is the photo detector? It is absorbing light and giving some electrical signal. Okay, if it is too sensitive to absorb small amount of light and converting into electrical signals, it is possible to harvest the energy, right? Then it can be harvested and can be converted into electrical energy, right? In a high scale, we are just scaling up the photo detector into OLED solar cells. That's all. So this is one of the major advanced applications right now. The research is progressing. Next slide, please. So we have already given that classification. Next slide, please. So this is one of the first organic solar cell. It is formulated by researchers. We have given the reference in this slide. You can, if you have some interest, you can go through that slide. These type of molecules will absorb sunlight, okay, and it will try to harvest solar light and it will convert into electrical energy. The beauty of organic solar cells is it will try to reap out all the wavelengths of sunlight. For example, if you think of the chlorophyll, so it will absorb only in the red region. That's why our leaves are appearing as a green. Okay, but the solar cells can be made as a molecularly imprinted polymer. Okay, by observing various wavelength molecules, we can design the molecules, various molecules, observing all the particular wavelengths, and we can arrange the molecules by printing in a polymeric sheets in a proper composition. All the wavelengths can be observed from the sunlight. So it is possible to utilize the maximum utilization of sunlight towards the solar energy conversion. Okay, this is one of the advanced application of photochemistry. Next slide, please. So this is also the same. In this process, there are four type of um, one is photon observed, and the excited state is also transfer substance, and so these are the four stages of organic solar cell. And the next slide, please. So the organic solar, the photon absorption and excited state different. That's the organic solar is some lacking. That is photo absorption. We have to improve photo absorption. Of course, it is on the way. Most of the efficiency of absorption of solar light is in hand. Okay, the transfer will easily can be handled. It can be pulled out. Okay, next slide, please. Okay, this is the efficiency limit of organic solar cells, where can be transferred, and what is the energy gap. We have to reduce the conduction band between from the energy difference between conduction band and the valency band. The work is on the progress. Next slide, please. So multiple junction cells. That is, this is one of the advanced form. That is, high energy band gap cells and low energy band gap cells are put together to perform simultaneously. That is, why the high energy band gap cells has to be used. For example, if if the radiation is between ultraviolet and this violet and near visible, that is blue radiation, then you need a higher energy band gap radiation. Okay? If you have some red light region, then you need a low band gap cell. If you are putting together, you can cover up almost all the wavelengths. Okay, that's why you are putting up these two wavelengths, these two solar cells put together. Okay, next slide, please. So we have already discussed this point. Next slide, please. So dye-sensitized solar cell is another concept where you can mix some organic and inorganic substances together, where you can do some ruthenium type of complexes and attaching these complexes on the solar and the semiconductor devices, semiconductors, that is nanoparticles maybe. So the band gap between the the band gap in the nanomaterials like CO2 semiconductors or SNO2 semiconductors, the band gap will be not it is in a navigable level. If you manipulate this band gap, you can inject electrons from the conduction valency band to conduction band. Okay, for that you need some energy. So to bypass this, we can attach and directly write the dyes and electrons, inject electrons to the conduction band to get some energy. This is the concept of dye sensitized cell. But dye-insulated solar cell is previous concept for organic solar cell. Okay, so now the both are developing, but anyway, dye-insulated solar cell concept is a old concept than the organic light emitting diodes. Okay, next slide please. So Michael Gratson is the first person who created the dye-insulated solar cell concept, in which he attached ruthenium dyes on PiO2 surface, and he used iodine triiodide electrolyte for a artificial electrolyte, that is to reduce back oxidized ruthenium dye. Okay, the 11% efficiency has been obtained in that time, that is in 2000 around, but 20 years back, 2000 to 2010. In that period, the dye-insulated solar cell concept has been evolved much. Okay, and variable steps involved in this concept has been given in this slide. Okay, next slide please. Okay, these are the 4 steps involved in the dye-insulated solar cell, and what we have seen is basic concepts of photochemistry on what is the light interaction between matter and light, and how the light is changing the properties of matter, and what are the concepts after activation. Okay, so the emitted light, how it is applied for the various applications. This is the basic concept of this talk. Okay, so we have seen that what is the application. First is laser application, and second one is LEDs, and then how the LED devices can be advanced to the higher level, like uh, display devices, and then how the devices can be manipulated into photodiodes, and these diodes, how the photodetectors, which is receiving a small amount of light, can be advanced to the higher level to reap out, that is harvest solar energy in a bigger scale. And then finally we have seen what is called the dye-insulated solar. These are the main applications of photochemistry, and if you have any questions, you can I'm happy to answer. Thank you very much.
Thank you, sir. Thank
Thank
you
you.
for the basics of photochemistry and its recent applications. Before going for discussion, I sincerely apologize for the network issues from our side. Now the
No
floor is
problem.
open for. Okay, sir. Thank you, sir. Thank you. Now the floor is open for discussion. If you have any queries, clarifications, you can ask Dr. Muthumareeswaran. He is ready to answer your doubts. Participants, if you have any doubts, any query, you can ask our professor. He is waiting to respond you. Sir, I have one small doubt because I'm an organic person, but during my perspective, what is that heterojunction, that that application, heterojunction diode?
Heterojunction organic diodes, right?
Yes, sir.
Yeah. It is just like a P-type and a N-type semiconductor.
Okay.
You have studied about semiconductor, you can use this easily. That is P-type semiconductor is nothing but a
With
positive
positive
charge
pole, positive
infused.
pole.
Yeah, hole will be there. Okay.
Ah,
If it is N-type semiconductor, then the negative hole will be there.
Yes.
Okay. Similarly, if it is if positive and the negative semiconductors are put together, it is called a PN junction. That is called the heterojunction. Okay. Similarly, in photoelectrodes, mostly they are conductive polymers. Okay. The conductivity can be generated by introducing some additional electrons like electron containing substance like nitrogen or oxygen. Okay. They have some double bonds. Sorry, non-bonding electrons. Okay. Therefore, they are electron rich. Sometimes they will introduce some electron deficient groups. Okay. Then they are. It will act as, if you put together these two substances, it will act as a PN junction, that is called heterojunction.
Okay, sir. Okay. Thank you, sir. Thank you for clarifying my
Thank you.
small doubt. If, is there any question, we'll come to the end of the session. I request our Professor Dr. A. Balakrishnan, Head Administration, to proceed for the vote of thanks. Over to you, sir.
Thank you.
Very good evening to all. Myself, Dr. Balakrishnan, one of the convener of this faculty development program. It's very immense pleasure to propose the vote of thanks in the last day of faculty development program. On behalf of Mohammed Sadek Management, principal, staff, I would like to thank today's chief guest, Dr. Muthumareeswaran sir, Assistant Professor, Department of Chemistry, CUG Campus, Anna University, for his valuable informative sessions. Really, it's very useful for us. And I would like to thank all the resource persons for this faculty development program for spending spending their valuable time with us. This is the last day of our faculty development program on recent advances and applications of chemical sciences. Yesterday, Dr. Gnanakum, head of physical chemistry, Madhuri Kamaraj University, joined with us and given a wonderful lecture on electrochemical mechanism in energy conservation devices. It was very really interesting one. Then second day, Dr. Yelumalai sir, Professor, Department of Green Energy Technology, Pondicherry University, has given his informative talk. Then on the third day, Dr. Ramesh Ardas, Professor, Department of Chemistry, gave Mugam sir, and all my department faculty friends, Dr. J. Bala ma'am, Professor, Dr. Chandramal Chelvi ma'am, Associate Professor, Dr. Sweeta ma'am, Professor, and Mrs. Nitya ma'am, Assistant Professor, for their continuous support to conduct the event in grand manner. I also thank Mr. Syed Hamid, System Admin, for his technical support for all 5 days. I extend my sincere thanks to all the participants from various educational institutions and research organizations for their continuous passion for all 5 days. So once again, I thank you all. Thank you.
Thank you, sir. Thank you, sir.
Devbalam